Welcome to this video on quantum computing, where we will explore the physical architecture and key components of these revolutionary machines. This overview is prepared by Dr. Qureshi from NUS. In this video, we will cover two main topics. First, the fundamentals of quantum computers and how they differ from classical ones. And second, a deep dive into the hardware, including the QPU, electronics, and cooling systems. What is a quantum computer? Unlike classical machines, they use quantum mechanics and qubits to process information, allowing them to solve complex problems that are practically impossible for traditional supercomputers. Quantum computing relies on three core principles: superposition, where a qubit can be in multiple states; entanglement, linking qubits together; and interference, which helps amplify the correct answers. Quantum computers represent a paradigm shift. While classical systems process information linearly, quantum computers calculate multiple pathways simultaneously, finding mathematical shortcuts that classical physics simply cannot. This table highlights the differences. Quantum computers use probabilistic qubits rather than deterministic bits, offer exponential scaling power, operate at near absolute zero, and are ideal for chemistry and cryptography. Now let's take an intricate look at the actual anatomy of a quantum computer. Physically, these machines are impressive. They include chandeliers, which are dilution refrigerators, the quantum processor chip itself, and sometimes a laser grid for specific setups like trapped ions. The quantum processing unit, or QPU, is the heart of the system. Analogous to a classical CPU, it is the engine where quantum information is stored, manipulated, and processed. The QPU's role is to maintain delicate states like superposition and entanglement. Because they are highly sensitive to environmental interference, they require precision engineering and advanced cleanroom fabrication. As noted in the SpinQ architecture overview, qubits are the fundamental units of quantum computation, capable of representing both 0 and 1 simultaneously. There are different ways to create qubits. Superconducting circuits are currently the most widely adopted architecture, while trapped ions use charged atoms in a vacuum to achieve high fidelity and coherence. Other modalities include photons, which are highly resistant to noise and great for networking, and quantum dots, which manipulate electron spin for high levels of potential miniaturization. Quantum gates are the operations that manipulate these qubits. Unlike classical logic gates, they work with probabilistic amplitudes to execute complex quantum algorithms. Finally, on-chip interconnects are essential. They provide the complex routing needed for communication between qubits, and designing them to minimize noise is key to scaling quantum processors. Moving to control systems, these are the conductors of the quantum symphony. They generate and deliver the highly precise microwave, radio frequency, or laser signals needed to manipulate qubits. Without them, the QPU remains inert. Control electronics must provide precision timing and signal generation, physically executing quantum gates defined by software. As qubit counts increase, the primary challenge is scaling these systems to manage thousands of signals without generating excess heat. Speed and precision are vital. For superconducting systems, typical gate times are around 10 nanoseconds. Control electronics must tune these microwave pulses with exact phase and amplitude, separating successful calculations from destructive quantum noise. Next, we explore the extreme environment. Qubits require a specialized cryogenic infrastructure to function reliably. The dilution refrigerator, often called the golden chandelier, isolates quantum hardware from thermal and electromagnetic noise. By using a mixture of helium-3 and helium-4, it cools the system down to near absolute zero, where the QPU resides. Operating at around 15 millikelvins, these computers are colder than deep space. At such extreme temperatures, thermal vibrations cease, which is essential to prevent the delicate quantum state from collapsing. The cryogenic system provides three critical functions: enabling superconductivity in metals, isolating the processor from thermal and electromagnetic radiation, and filtering incoming signals to ensure only clean control pulses reach the QPU. Quantum error correction, or QEC, is a vital component. Because the quantum states are fragile and cannot be copied due to the no-cloning theorem, QEC infrastructure is used to detect and fix errors in real time. QEC is essential because qubits are highly sensitive to environmental interference, like radiation or magnetic fields. Without it, the decoherence of quantum states leads to inaccuracies that prevent scaling to larger, more useful systems. QEC works by encoding one logical qubit across many physical ones, providing the redundancy needed to detect faults. Ancillary circuits then measure error syndromes, allowing the system to apply corrections while preserving the logical state. The classical interface acts as a vital bridge. It processes input and output data, executes complex control logic, schedules algorithms, and performs the rapid calculations required for real-time error syndrome monitoring. Finally, Quantum interconnects transmit quantum information across distances. They are crucial for linking multiple QPUs to act as one large modular processor and form the foundation for a future networked quantum internet. With these components understood, we can look at the real-world impact of these machines. Quantum computing holds immense promise for industries like biomedicine, where it can simulate molecular interactions for drug discovery, fintech for complex financial modeling, and artificial intelligence for training massive models. Furthermore, quantum systems will optimize supply chain logistics and drive progress in materials science. It also forces a shift in cybersecurity, as quantum algorithms necessitate new post-quantum cryptography standards to protect our data. Looking ahead, we face significant challenges in the path toward truly fault-tolerant quantum computing. We must address technical and practical hurdles before these machines can reach their full potential. Key bottlenecks include the decoherence problem, managing heat loads from complex control wiring, the immense cost of cryogenics, and the need for more mature quantum software and specialized talent. We are currently in the NISQ era, where noise limits algorithm depth. The industry's primary goal is reaching a fault-tolerant state, where massive arrays of logical qubits drive error rates low enough for broad quantum advantage. The evolution of quantum technology follows a clear path, moving from the current noisy, small-scale NISQ systems toward logical qubit demonstrations, and finally, to massive, fault-tolerant machines. Thank you for watching this video. We are unlocking the future of computation together. For those interested in collaborating, please reach out. Dr. Imfahed Qureshi is open to consulting, research proposals, and technical training. You can contact him via email or visit the CQT web hub and professional network links provided.